There's no centers in this part because we're grinding the inside diameter. So we're gonna have to hold it with our 3-jaw chuck. Now to ensure that our ID grinding is straight to the axis, we're gonna have to grind the OD of this part because this was all 3D printed. These rough surfaces are not accurate enough to be able to hold our part center. So we had to hold on to the small OD to grind the large OD. Then we had to hold the large OD so that we could grind the inside profile. Since it's larger on this side and smaller on this side because of the taper, we wanted the large side facing out so our wheel could come in, we can angle it in and give us the taper that we needed on the inside of this polygon. This is our CBN ID grinding wheel. Now, it looks like a bar, but that's actually called a grinding wheel. This is what we use to grind the inside surface of our polygon. Since this had never really been done and we didn't have any in-process gauging, we had to use our OD part to actually see if we ground this correctly. And we were running that spindle at 32,000 RPM. You can imagine a wheel that's 2 1/4 inches long coming into a part that's about 2 1/4 inches deep, running at 32,000 RPM. There's a lot going on. We had to make sure that everything was perfect before we started. Since we're using the ID wheel, we're using a rotary diamond dresser on the swing arm to be able to reach it and dress our ID wheel. Using the correct geometries, we trusted our machine, the Studer S41 from United Grinding, more than capable of hitting millionths of an inch. We got as accurate as we could, brought the ID to its nominal dimension. We have the need to utilize sophisticated grinding equipment to try and grind these 2 3D printed 718 Inconel parts that were very raw and very rough. And when you look at these, they don't look like much, simple parts, but in fact, they are very complicated. We have an OD part and an ID part that have to come together. And the only way we're gonna do that with 3D printed parts is a post-process with a cylindrical grinder. We decided to hold this part between centers. I have centers drilled in this part so we can hold it between our workhead and our dead tailstock. We got 2 brand new Royal centers. Thank you, Royal, for sending those to us. That's gonna be the perfect thing we need to hold this part rigidly between centers. So the wheel we're using is a Tierlet CSS Ultra 60 grit wheel with ceramic in it. That 60 grit's gonna be perfect for this 718 Inconel because it's really hard. We're gonna want a softer wheel. So one of the complications we had with this machine is checking clearance to make sure that we could get every single contour on this. This part actually, we had to flip it once or twice because we did the big OD first. We flipped it, did the small OD with the shoulder, and then we were able to do the polygonal taper. We have a specially made oil coolant nozzle just for this part that reaches the exact width of our wheel, and it gave us a perfect stream of grinding oil that was injected directly into our cut to give us that lubricity that we needed. Bringing the wheel in on this was incredibly complicated because we're trying to follow this polygonal shape, and usually with an eccentric circle, it's kind of easy to see, but since this is rotating on the C and the X is moving in and out, we had to bring it in 2 inches, an inch, 3/4 of an inch, and watch it to see if that wheel is following the lobes properly, going in on the flats and out on the lobes. And we walked it in and walked it in and walked it in, and then we let the wheel do its thing. So we took a 1/10 per pass grinding this. It had 20 thousandths on it, so it took quite a long time, but that was okay because we're doing a pathway part, right? We're trying to feel out what this machine is capable of. We didn't know how this material was gonna react with a wheel running at 8,000 SFM. So we took very light passes. We actually didn't see any sparks, which was great, and that gave us a really beautiful finish. We actually got a 14 RA finish on this part. So let me talk a little bit about the programming. When you're using the HSM programming in Studer, we took a cross-section of our polygonal taper and created that profile into a DXF at the nominal dimension. If this was datum A, this profile is called out 1/2 an inch from this datum. So we cut the part in CAD, created a 2D geometry DXF of that profile, imported that into Studer, and that's the toolpath the wheel's following. We got as accurate as we could, and then we took the OD part, and they fit perfect. As our society and our industry pushes to go to Mars, to get rockets into outer space, and to put people into orbit, they come up with new technology that are almost all 3D printed out of super alloys. As you know, with additive manufacturing, there's always a post-process, but we're pushing the limits with additive manufacturing because it's easier and we can make more things that are more complicated, things that subtractive manufacturing can't always do. When we're limited to tooling or certain geometries, 3D printing breaks beyond that, so we can use more complicated surfaces and profiles to create whatever it is we need to create. So I hope you guys enjoyed that. Some crazy stuff. I got 3D printed 718 Inconel and the Studer S41 from United Grinding, putting some incredible finishes on this, bringing us to crazy tolerance. It's so exciting to see what's going to happen in the future, where we're marrying all these different manufacturing processes to accomplish our goals. If you guys like what you saw, please like and subscribe, and we'll see you next time. Now they're stuck.
Not as strong as you once were. We'd see the CIA get you pushing pencils.